Hello, in this lesson we are going to study the superposition of waves. First we will study the phenomenon of interference in general, and then the particular case of standing waves. In a medium, two or more waves coming from different sources can propagate at the same time, and it may happen that at some point in the medium these waves coincide. What would happen then? Well, the principle of superposition is fulfilled, which says that when two or more waves combine, the resulting wave is the algebraic sum of the individual waves. In the figure we see two wave pulses, 1 and 2, moving in opposite directions on a string. The shape of the string, when the two pulses meet, is obtained by summing the amplitudes of each pulse, as observed at different time instants. The simplest case we can study is that in which two harmonic waves with the same frequency and direction of propagation interfere at a point P. The first wave has its focus here, at a distance x1 from point P, while the second wave has its focus here, at a distance x2. At point P, the amplitude of the first wave is given by I sub 1, equal to A sub 1 sine of omega t minus kx1. We will call kx1 phi sub 1. However, at point P, the amplitude of the second wave is I sub 2 equal to A sub 2 sine of omega t minus kx2. We will call kx2 phi sub 2. According to the superposition principle, the amplitude at P is the sum of I sub 1 plus I sub 2, which is a sine of the same frequency as the interfering waves. With respect to its amplitude A, is this square root that we see here, which we see depends on the cosine of phi sub 1 minus phi sub 2, which we will call cosine of phi sub 0. So, the amplitude of the resulting wave after interference will depend on the value of the cosine of phi sub 0. For example, it will be maximum when this cosine of phi sub 0 is 1. For this, the angle has to be a whole number of times 2 pi radians, and that assumes that x2 minus x1 must be an even number of half lambda. In this case, we say that the interference has been constructive, and the value of the amplitude will be the sum of the amplitudes of the original waves, A sub 1 plus A sub 2. When the cosine of phi sub 0 is worth minus 1, then the amplitude of the resulting wave will be minimum. For this, the angle phi sub 0 has to be an odd number of times p radians. And in this case, x2 minus x1 would have to be an odd number of half lambda. This is the case of destructive interference, in which the amplitude of the resultant wave will be minimal and will have as its value the absolute value of A sub 1 minus A sub 2. In this transparency, J observed how some balls oscillate up and down in the sea after the waves have passed through this double slit. This row of balls is located on points where there has been a constructive interference and the amplitude is maximum, while these others are over points where the interference has been destructive and the amplitude is minimal. If we look, the geometric location of the points with constructive interference are hyperbolas. We have painted this time in red. The points where there has been destructive interference also form a hyperbola, in this case painted in white. Here we see the phenomenon from another perspective. This example represents an experiment in which we illuminate this double slit with a laser. If at a certain distance we put a screen on which the light is projected, this interference pattern is observed, in which we see that the intensity maxima coincide with the points where there has been an interference, with the points where there has been a constructive interference, represented in this case by hyperbolas with a continuous orange line, while the points in shadow with minimum intensity correspond to the hyperbolas of minimums represented with green dashed lines. In this other example, we have represented two loudspeakers emitting the same tone from two different positions. One is here and the other here. If the paths traveled by the two waves to the microphone are equal, we see that the signal received by the microphone is a maximum. And it is the same if the difference of paths is a full wavelength. We see it, for example, there. However, if the difference of paths is half a wavelength, the signal received by the microphone will be minimal, which is this case. Let us now move on to explain standing waves. They are a particular case of interference and occur when two harmonic waves of the same frequency, amplitude, speed, and nature are combined and propagate in the same direction, but in opposite directions. The green wave, we see that it propagates to the right, in the increasing sense of the axis. So its mathematical expression is I1 equal to sine of omega t minus kx. The wave traveling to the left, in blue, is represented by I2 equal to sine of omega t plus kx. The red wave is the sum of both, and we see that it does not travel, hence it is called a standing wave. It has some fixed points where the amplitude is 0, which are called nodes, and some points where the amplitude is maximum, which are called bellies. To see where these nodes and these bellies are, let's apply the trigonometric relation sine of a plus sine of b equal to twice cosine of a minus b over 2 by sine of a plus b over 2. Applying this property, we are left with the resulting wave equal to twice a times cosine of kx times sine of omega t. That is a sine of equal frequency to the interfering waves, and its amplitude is a periodic function of position, which we have called a of x. The points at which this amplitude a prime is minimum are called nodes. These take place when the cosine of kx is 0, i.e., where kx is an odd number of times b over 2, and therefore x is an odd number of lambda fourths. In the standing wave on the screen, we see marked the points where the nodes occur, separated from each other a half wavelength. The points where the amplitude is maximum are called wombs. These occur when the cosine of x is either plus 1 or minus 1, i.e., where k is an integer number of times pi, and therefore x is an integer number of lambda over 2. In the standing wave on the screen, we see marked the positions where the wombs occur, separated from each other a half wavelength. Finally, let's look at the creation of standing waves by vibrating a string. The vibration frequencies that give rise to standing waves are called resonance frequencies. The lowest is the fundamental frequency, and we can see it in this video, where the string is excited at this extreme by an oscillation of 12 Hertz. This is the first harmonic at 24 Hertz, in which we see a null and two bellies. And this is the second harmonic at 36 Hertz, with two nulls and three bellies. And this has been all. I hope you liked this lesson on interference and standing waves.